Chapter 2. Pace and Nervous System Control. The speed at which food is consumed alters the state of the nervous system, and that state determines how much of a digestive sequence is allowed to operate. Eating is not just the delivery of material into the gut. It is a signal that either permits or constrains the system that processes that material. When pace is rapid, the body interprets the environment as unstable or urgent, and sympathetic activity rises. This shifts control away from digestion and reduces the output of acid, enzymes, and bile before the system has had time to prepare. When pace is slower and controlled, parasympathetic signaling increases, and the system is given the conditions required to initiate digestion with sufficient output. The difference is established before the stomach receives the first portion of food. Rapid intake compresses the preparatory phase into a narrow window that the system cannot fully utilize. Sensory input from taste, smell, and texture is reduced because food is moved quickly through the mouth, limiting the activation of neural pathways that prime gastric secretion. Salivary output decreases, and mechanical breakdown is incomplete. Larger particles enter the stomach, increasing the workload required for chemical processing. At the same time, the stomach has not yet increased acid production to levels that can compensate for this additional demand. The sequence begins with a mismatch between input and capacity, and that mismatch propagates through the rest of the system. Gastric function is directly affected by this compression. Acid secretion depends on both anticipatory signaling and continued neural input during eating. When pace is rapid, the stomach receives a larger volume of material before acid output has reached effective levels. Proteins are exposed to a higher pH environment and remain partially folded. The stomach may respond by delaying emptying to allow more time for processing, which increases retention and the likelihood of fermentation. In other cases, material is passed forward before it has been adequately prepared, shifting the burden to the small intestine. Both outcomes reflect the same constraint. The stomach was not given the time or signaling required to match output to input. Pancreatic and biliary responses are similarly affected. Enzyme release and bile flow are coordinated with the arrival of partially processed material from the stomach. When large volumes of inadequately prepared food enter the small intestine quickly, this coordination is disrupted. Enzymes may be insufficient relative to the load, and bile release may not align with the presence of dietary fat. Lipids remain in larger, less organized forms, and proteins and carbohydrates are not fully reduced. The intestine is forced to handle material that exceeds its optimal processing range, leading to changes in motility, fluid balance, and microbial activity. Pace also influences motility through its effect on neural control. Rapid eating is associated with irregular contraction patterns that reduce the efficiency of mixing and propulsion. The system may alternate between slowed and accelerated transit as it attempts to manage the incoming material. Slowed transit increases retention and fermentation, while accelerated transit reduces absorption and increases variability in nutrient delivery. These patterns are not fixed but reflect the system's attempt to compensate for the initial mismatch created by rapid intake. Over time, consistently rapid eating trains the system into a constrained operating mode. The nervous system begins to associate food intake with a state that suppresses digestive output. Baseline secretion decreases and coordination between organs weakens. The system adapts to processing food under these conditions, but the adaptation reduces overall capacity. Symptoms become more consistent because the system is consistently starting from a reduced baseline. Slowing the pace of eating changes the system before it changes the food. Extended sensory exposure increases parasympathetic signaling, allowing salivary secretion, gastric acid production, and anticipatory enzyme release to rise before the stomach receives a significant load. Mechanical breakdown improves, reducing the size of particles that require chemical processing. The stomach is able to match acid output to incoming material, and the sequence begins with a more favorable alignment between input and capacity. Downstream processes then operate on substrates that have been properly prepared, reducing the need for compensation. Pace is not a minor behavioral detail. It is a control variable that sets the operating conditions of the digestive system. When pace supports parasympathetic dominance, the sequence can proceed with the timing and output required for complete transformation. When pace reinforces sympathetic dominance, the system begins under constraint and carries that constraint through every stage. The outcome is determined less by what is eaten and more by the conditions under which the system is asked to process it. Rushed eating and sequence disruption. Rushed eating compresses the early stages of digestion into a time window that is too short for the system to prepare itself, and that compression alters the entire sequence that follows. Digestion depends on ordered transformations that begin before food reaches the stomach. Sensory input from chewing, taste, and smell activates neural pathways that increase salivary flow, initiate gastric acid production, and coordinate downstream secretion. When food is consumed quickly, this preparatory phase is truncated. The system receives volume before it has generated the output required to process that volume, and the sequence begins with a deficit that cannot be corrected later. Mechanical breakdown is the first point of disruption. Inadequate chewing leaves food in larger particles with less surface area exposed to digestive fluids. These particles enter the stomach requiring more intensive chemical processing at a time when acid production has not yet reached effective levels. The stomach is forced to operate on material that is both structurally intact and poorly timed relative to its own secretory capacity. Proteins are not fully unfolded, and the initial transformation that enables enzymatic access is incomplete. The material that exits the stomach carries this structural resistance forward, increasing the burden on the small intestine. Gastric timing becomes unstable under these conditions. The stomach must choose between delaying emptying to compensate for incomplete processing or moving material forward to prevent excessive retention. Delayed emptying increases the opportunity for fermentation and pressure buildup, while accelerated emptying transfers inadequately prepared material into the intestine. Both outcomes originate from the same disruption. The stomach did not receive sufficient time or signaling to align acid output with incoming food. The sequence loses synchronization at its first major processing step. Downstream systems inherit this mismatch. Pancreatic enzymes are released based on signals that assume a certain level of preparation has already occurred. When that preparation is incomplete, enzyme activity is less effective because substrates remain structurally resistant. Bile release may not align with the arrival of dietary fats, leaving lipids insufficiently emulsified and difficult to absorb. The small intestine receives material that exceeds its optimal processing range, and it responds by altering motility and fluid balance. Segmentation becomes less efficient, and peristalsis may either slow to allow more time for breakdown or accelerate to clear material that is not being handled effectively. This disruption extends into the microbial environment. Larger, partially processed substrates provide a greater supply of fermentable material, increasing gas production and altering the composition of microbial activity. The intestine is exposed to compounds that would not be present in significant amounts if upstream processing were complete. These changes feed back into motility and barrier function, increasing variability in symptoms and reducing overall stability. What appears as bloating, discomfort, or irregularity is the downstream expression of a sequence that began without proper alignment. Rushed eating does not simply reduce efficiency at one point. It shifts the entire system into a pattern of compensation. Each stage adjusts to the deficiencies of the previous one, but those adjustments introduce new constraints that propagate forward. Over time, this pattern can become habitual, lowering baseline output and weakening coordination between organs. The system becomes accustomed to operating under conditions where preparation is incomplete and timing is inconsistent. Restoring sequence integrity requires restoring the conditions that allow preparation to occur before volume arrives. Slower eating increases sensory exposure, strengthens neural signaling, and allows secretory output to rise in advance of gastric loading. Mechanical breakdown improves, reducing the demand placed on chemical processing. The stomach can align acid production with incoming material, and downstream systems receive substrates that have been properly prepared. The sequence stabilizes because each step is given the conditions required to perform its role before the next begins. Training the nervous system into constrained digestion. The nervous system does not treat each meal as an isolated event. It adapts to repeated patterns and establishes a baseline state that reflects how digestion is usually performed. When food is consistently consumed under conditions that suppress parasympathetic activity, the system learns to associate eating with reduced output. This is not a conscious process. It is a gradual recalibration of neural signaling that lowers secretory capacity, disrupts timing, and weakens coordination between digestive organs. What begins as a temporary constraint becomes the default operating mode. This training occurs through repetition of mismatched input and state. When meals are eaten quickly, under stress, or without sufficient sensory engagement, the nervous system does not fully activate the pathways that drive digestion. Acid production remains lower, enzyme release is less synchronized, and bile flow becomes inconsistent. The system processes food under these conditions and adapts to make that constrained processing more stable. Over time, glands reduce their baseline output because they are not being regularly stimulated to operate at higher levels. The system becomes efficient at functioning within a limited range, but that efficiency comes at the cost of overall capacity. Gastric function reflects this adaptation clearly. Acid secretion is not only a response to immediate signals, but also a function of baseline readiness. When the stomach is repeatedly asked to process food with reduced neural input, its capacity to generate strong acid responses declines. Proteins are routinely exposed to suboptimal acidity, and the system normalizes this level of processing. Downstream organs adjust accordingly. The pancreas releases enzymes into an environment where substrates are not fully prepared, and the intestine develops motility patterns that attempt to manage partially processed material. The entire sequence shifts to accommodate the initial constraint. This adaptation extends beyond secretion into timing and coordination. The precise alignment between stomach emptying, enzyme release, and bile flow depends on consistent signaling patterns. When those patterns are repeatedly disrupted, the synchronization between organs weakens. Enzymes may be released too early or too late relative to incoming material, and bile may not be delivered in a way that supports effective fat emulsification. The system continues to function, but it does so with reduced precision, increasing variability in outcomes and lowering the threshold for disruption. The result is a system that appears sensitive and inconsistent, but is actually operating according to a learned pattern. Foods that require higher processing capacity produce symptoms because the system has been trained to operate below that capacity. Even when conditions improve temporarily, the underlying baseline remains constrained, and the system returns to its habitual mode of operation. This creates the impression that improvements are short-lived or dependent on strict control of inputs. Reversing this pattern requires retraining the nervous system through repeated exposure to conditions that support full digestive output. Slower eating, consistent sensory engagement, and reduced sympathetic activation provide the signals required to increase parasympathetic tone. As these signals are repeated, secretory glands begin to increase baseline output, and coordination between organs improves. The system relearns how to initiate digestion with sufficient capacity and proper timing. This process does not occur instantly. It reflects the same adaptive mechanisms that created the constraint, but in the opposite direction. As the nervous system shifts, the entire sequence begins to reorganize. The stomach produces stronger acid responses, enzymes are released in alignment with incoming material, and bile flow becomes more consistent. Motility stabilizes because the system is no longer compensating for incomplete preparation. The digestive process becomes more predictable because it is being driven by a control state that supports full function rather than limiting it. Long-term cost of speed on digestion. Consistently eating at high speed does not just disrupt individual meals. It reshapes the baseline performance of the digestive system over time. The body adapts to the conditions it is repeatedly exposed to, and when those conditions involve compressed eating, reduced sensory engagement, and elevated sympathetic activity, the system recalibrates toward lower output and weaker coordination. What begins as a temporary mismatch between input and processing capacity becomes a stable operating pattern in which digestion is routinely initiated under constraint. The first cost appears at the level of secretion. Gastric acid production is driven by neural signaling that reflects both immediate input and habitual patterns. When meals are repeatedly consumed quickly, the preparatory phase is shortened, and the stomach is not consistently stimulated to reach higher levels of acid output. Over time, this reduces baseline acid capacity. Proteins are exposed to a less acidic environment, and the initial transformation that enables enzymatic access becomes incomplete by default. The pancreas then releases enzymes into a system where substrates are not fully prepared, lowering the efficiency of breakdown and increasing the amount of partially processed material that moves into the intestine. Bile dynamics are also affected. Rapid intake disrupts the timing signals that coordinate gallbladder contraction with the arrival of dietary fat. When this pattern is repeated, bile release becomes less precise, and fats are not consistently emulsified into structures that can be absorbed efficiently. Lipids pass through the small intestine in larger, less organized forms, altering both nutrient absorption and the composition of material that reaches the colon. This shift changes the internal environment, increasing reliance on microbial processing of substrates that should have been handled earlier in the sequence. Motility adapts in response to these upstream inefficiencies. When the system is consistently presented with inadequately prepared material, it develops patterns that attempt to manage that condition. Transit may slow to allow more time for breakdown, leading to increased retention and fermentation, or it may accelerate to clear material that cannot be processed effectively, reducing absorption. These patterns can alternate because the system is not stable. It is responding to variable levels of incomplete processing. Over time, this variability becomes more pronounced and digestive outcomes become less predictable. The intestinal barrier is exposed to a higher load of partially processed fragments as this pattern continues. Larger molecules that would normally be reduced earlier in the sequence interact with the lining of the intestine, increasing the likelihood of immune activation. This does not occur as a primary dysfunction, but as a response to material that has not been properly prepared. The immune system adjusts to this increased exposure, and inflammatory signaling becomes more frequent. This adds another layer of instability as immune activity feeds back into motility, secretion, and neural signaling. Energy extraction becomes less reliable as well. Incomplete breakdown and inconsistent absorption lead to fluctuations in nutrient availability. Amino acids may be delivered in uneven patterns, fats may not be fully absorbed, and fat-soluble vitamins depend on bile-mediated transport that is no longer consistent. The system continues to receive input, but the conversion of that input into usable material becomes variable. This variability extends beyond the digestive tract, affecting systemic processes that rely on steady nutrient delivery. These changes do not occur abruptly. They accumulate through repetition. Each meal consumed under constrained conditions reinforces the same pattern, gradually lowering capacity and weakening coordination. The system becomes efficient at operating within these limits, but that efficiency masks a reduction in overall function. Foods that once required minimal effort to process begin to produce symptoms because the system is no longer capable of completing the sequence at the required level. Reversing the long-term cost of speed requires restoring the conditions that allow full engagement of the digestive system. Slowing the pace of eating reintroduces the preparatory phase, increases parasympathetic signaling, and allows secretion to rise before the stomach receives a significant load. As this pattern is repeated, baseline output begins to increase and coordination between organs improves. The system gradually shifts back toward a state where each stage prepares the next, reducing the need for compensation and restoring stability across the entire sequence. Calm eating as capacity restoration. Calm eating alters the control layer that determines how much of the digestive system is allowed to operate, and this change in control increases capacity across the entire sequence. When the body enters a state that supports parasympathetic activity, secretory output rises, timing between organs becomes more precise, and blood flow is directed toward the gastrointestinal tract. These changes are not superficial. They directly affect the system's ability to perform the transformations required to convert food into absorbable material. Capacity increases because the system is no longer operating under constraint. The preparatory phase expands under calm conditions. Sensory exposure to food is extended, allowing neural signaling to build before a significant volume reaches the stomach. Salivary secretion increases, initiating early enzymatic activity and improving mechanical breakdown through more effective chewing. Particles entering the stomach are smaller and more uniform, reducing the demand placed on gastric processing. At the same time, gastric glands are activated in advance, and acid production begins to rise before the first substantial input arrives. The system aligns output with incoming material instead of reacting after the fact. Gastric function improves as a result of this alignment. Acid levels reach the threshold required to alter protein structure consistently, exposing peptide bonds for enzymatic cleavage. The stomach is able to process material efficiently without relying on prolonged retention or premature emptying. The material that exits the stomach is chemically prepared for the next stage, reducing the burden placed on the small intestine. This shift at the first major processing step propagates forward, improving the efficiency of the entire sequence. Pancreatic and biliary responses become more coordinated when the system is operating under calm conditions. Enzyme release is synchronized with the arrival of partially processed material, allowing macromolecules to be reduced to absorbable units before they move deeper into the intestine. Bile flow aligns with the presence of dietary fat, organizing lipids into emulsified structures that can be transported across the intestinal lining. These processes depend on timing as much as on quantity. Calm eating restores that timing, allowing each stage to prepare the next with greater precision. Motility stabilizes because the system is no longer compensating for incomplete preparation. Coordinated contractions mix and propel material in patterns that maximize contact with digestive surfaces without excessive retention or premature transit. The intestine receives substrates that are closer to their absorbable form, reducing the need to adjust transit speed in response to poorly processed material. This stability extends to the microbial environment, where reduced availability of large, fermentable substrates decreases gas production and variability in internal conditions. Repeated exposure to calm eating conditions retrains the nervous system and increases baseline capacity. Secretory glands respond to consistent stimulation by increasing output, and coordination between organs becomes more reliable. The system begins to initiate digestion from a higher starting point, reducing the likelihood that any given meal will exceed its processing limits. Foods that previously require restriction can be handled with less disruption because the system has regained the ability to complete the required transformations. Capacity restoration through calm eating does not rely on altering the food itself. It relies on restoring the conditions under which the system operates. As parasympathetic signaling becomes more consistent, the digestive sequence regains its structure. Each stage performs its role with sufficient output and timing, and the system transitions from compensation to coordinated function. Why early focus should be state, not food. The first constraint on digestion is not the composition of the meal, but the condition of the system that receives it. If the control layer is set to suppression, every downstream process begins below capacity. Acid output is reduced, enzymes are released with poor timing, bile flow loses alignment with fat intake, and blood is diverted away from the gut. Under these conditions, even simple inputs arrive at each stage in a partially prepared state. Changing the food does not correct this starting deficit. It only changes what is being processed under the same constraint. State determines whether the sequence can initiate with sufficient output. When parasympathetic signaling is present, secretion increases before significant volume reaches the stomach, and the system aligns preparation with input. Proteins encounter an acidic environment that unfolds structure early, enzymes meet substrates that are accessible, and bile arrives when lipids require organization into transportable forms. When this state is absent, the system reacts after the fact. The stomach attempts to increase acid after material has already arrived. Enzymes are released into an environment that has not been properly prepared, and bile flow may not match the presence of dietary fat. The sequence begins out of alignment, and that misalignment carries forward. Focusing on food first reduces demand but does not restore capacity. Removing inputs that are difficult to process can lower symptom intensity because the system is no longer being pushed beyond its limits. The underlying outputs remain unchanged. Acid remains low, enzyme release remains inconsistent, and bile flow remains poorly timed. As long as these constraints persist, the range of tolerable foods stays narrow. Over time, the threshold for disruption can drop further because the system has not been trained to operate at higher capacity. State-first correction changes the system before it changes the input. Increasing parasympathetic tone raises baseline secretion, improves coordination between organs, and directs blood flow toward the tissues responsible for processing and absorption. The same meal that previously exceeded the system's limits can now be handled because the transformations required to process it are being completed. Downstream variability decreases because material is no longer entering each stage in a compromised form. This approach also stabilizes feedback. When the sequence operates with sufficient output, the signals that regulate motility, secretion, and absorption become more consistent. The intestine receives substrates that are closer to their absorbable form, reducing the need for compensatory changes in transit speed. Microbial activity shifts because less fermentable material is available. Immune exposure decreases as fewer large fragments reach the barrier. These changes emerge from restoring the starting conditions rather than from selecting a narrower set of inputs. Prioritizing state establishes a foundation on which food quality can then have its intended effect. Once the system can perform the required transformations, differences in input composition begin to matter in a meaningful way. Nutrient density can be realized because nutrients are being fully extracted and transported. Without that foundation, quality remains unrealized potential. The system limits the outcome regardless of the input. Early focus on state aligns intervention with the structure of digestion. It addresses the control layer that determines whether the sequence can operate at all. When that layer is restored, subsequent adjustments to food become additive rather than compensatory, and the system moves toward stable, predictable function.